Welcome to my presentation on higher order derivatives, shapes of curves, and the second derivative test. So, a brief history of differentiation in general. It was invented by Gottfried Wilhelm Leibniz and Isaac Newton. They both invented this idea of differentiation. However, both ended up claiming that each other had stolen their work, so to this day it's not quite clear who actually came up with the idea first, but they both played a hugely important role in the development of this theory. What is differentiation? Well, differentiation is used to measure sensitivity to change of a function value with respect to a change in its argument. In other words, it allows us to find rates of change, and an example of this is acceleration, which is a rate of change, and the way we calculate that is by taking the change of velocity against time to find the rate of change, which is acceleration. We can visualize this on a graph where we have a curve, and the rate of change with respect to x is shown by the gradient of that curve at a specific point. We find the gradient at that specific point by drawing a tangent, the red line, and we find where it intersects with the curve and measure the gradient of that point using differentiation. A function can have many derivatives, and for example, the first derivative is a measure of how fast a function is changing over time, aka the slope of a function. It defines a function's velocity. Derivatives higher than the first order derivative are known as higher order derivatives. For example, the second derivative can be used to measure how fast the first derivative is changing, whilst the third derivative can be used to measure how fast the second derivative is changing. So for example, the second derivative can be used to measure acceleration, or therefore the third derivative would be used to measure the change in acceleration. And we can see in this table the notation of these higher order derivatives and what they're used for. So we can see velocity for the first, acceleration for the second, and then we can see jerk, snap, crackle, pop for all the other higher derivatives. They have many uses in real world applications that we will discuss later. And we can think of derivatives as functions themselves. So for example, if we have a function that is differentiable at some points belonging to the domain of that function, then the first derivative of that function is a function itself. Similarly, if that first derivative is differentiable at some points belonging to the domain of that first derivative function, then a second derivative function exists, defining the derivative of the first derivative function. And we can think of this pattern in mathematical notation by saying that the nth derivative is a derivative of the n-1th derivative of a function f. These derivatives have applications, and the second derivative can be used to determine any relative extrema in a function, aka it can be used to determine the nature of the function or the curve at the stationary point x0. This point can be found from the first derivative test. Assuming f is a function that is twice differentiable at this stationary point, we can then say if the second derivative of that function is greater than 0, then the function is said to have a local minimum at that stationary point. If it's smaller than 0, it has a local maximum, and if it's equal to 0, the test is said to be inconclusive, aka there could be a minimum, maximum, or a point of inflection. Here we can visualize what these terms mean. The local maximum defines the maximum height of that functional curve before it starts to decrease, and the local minimum represents the minimum height of that curve or function before it starts to increase. The saddle point represents where the function starts to level off. Okay, so let's see it in action. We have a function, and we want to find any local extrema of that function using the second derivative test. We first find the first derivative of that function, and once we found it, we set that first derivative to 0, which is the stationary point. We then want to find what the values of x are that we can plug into that first derivative to get it equal to 0. Having those x values, we then apply further differentiation to find the second derivative, and then we plug in each of those x values into that second derivative function to then come up with a value, and that value we then compare with 0 to see if it's greater or less than 0 or equal to 0. We here found that we had two local minimums at the specific coordinates and a local maximum, and we have therefore found all the local extrema of this function. The final topic is shapes of curves. A convex function has an increasing first derivative, whilst a concave function has a decreasing first derivative. And we can see this where the convex has a upwards bend and the concave has a downwards bend. If a function is twice differentiable on the open interval, then a function is convex on the open interval if the second derivative of that function is greater than 0, and is concave if the second derivative is smaller than 0. A very brief example shows we can check for the shape of a function by finding its second derivative and then seeing if it's greater than or less than 0. In this case it's greater than 0, so we found that this function is always convex. From the topics we've discussed today, looking at some real-life applications, we can see that second-order derivatives are used to measure acceleration of gravity and wind resistance. Some higher-order derivatives, such as the third derivative, known as jerk, is used in engineering, whilst the fourth, known as jounce, is used to study motion. And we can even use shapes of curves in economics to optimize processes within.